So let's start off by asking yourself which one is more elastic, steel or rubber? And most likely you're probably saying steel. So let's talk about this concept of elasticity. If we have an object and we kind of yank on it, then maybe it's going to undergo a change in shape or size. And the elasticity is going to be how much it changes given how much force. And to some degree how well it returns to the original shape. And materials that don't return to the original shape, we're going to call these guys inelastic, and we're not really going to talk about these guys so awful much. So one thing that is very elastic is going to be a spring, and we're going to kind of say that a free spring is going to be unstretched and it's not going to push or pull. So that's kind of my weak drawing of a spring. And if I went ahead and I kind of said, well, that's my spring, and I'm going to go ahead and I'm going to hang something on it, then it's going to distort the spring, and it's going to either push or pull, whether you compressed it or whether you stretched it out. In this case right here, this spring is going to pull. If on the contrary I had taken this spring and I had jammed on it with my hand and pushed it in that direction, then the spring is going to push back on me. So springs can generate force, and how much force is going to be directly proportional to how far you pull it. If you pull it kind of far, it's going to pull back. If you pull it really far, it's really going to pull back. Now, the force that it pulls back with is called the restoring force, and what it's trying to do is it's trying to restore itself back to its original shape. The expression that gives us the force as a proportional of distortion is actually called Hooke's law, and Hooke's law simply says that the force that a spring pushes or pulls with is going to be equal to negative k is just some spring constant, times x, where x is kind of the distortion. Now what this negative sign right here means is it's going to be in the opposite direction that it's stretched. So if this is kind of my unstretched spring, I'm going to call this side positive and I'm going to call this side negative, and I went ahead and I pulled this spring out such that it was at this level right here, then my distortion, my x, is going to be positive, and the force that the spring pulls on me with, that's going to be in this direction. I know the spring wants to return to that direction, so if the distortion is in this direction and the force is in this direction, we're simply calling the force negative, saying that it's in the opposite direction of distortion. And just kind of an example, now this spring constant, I forgot to mention on the last slide, it's going to have a unit of newtons per meter or newtons per centimeter, whichever one you're really kind of working with, but it's going to be a unit of force per unit length. And this is going to be my unstretched spring, and we're going to call this direction positive. So right over here, I've stretched this spring, and let's just for the sake of argument say that the spring constant is going to be 1 newton per centimeter, and here I've stretched it by 1 centimeter, so the force is going to be negative k times x, so it's going to be negative 1 newton. And again, all that negative sign means that the force is in that direction. You stretch this spring by 2 centimeters, so negative k times x, the distortion. The force is going to be negative 2 newtons, so it's going to be 2 newtons in that direction. What happens if I push on that spring? So now my distortion is negative, so negative 1 times negative 1 is going to give me a plus 1, so that tells me the force is in my positive direction. Now, as always, I'd like for you to go ahead and give this one a go on your own and be very careful here. The force is the weight, not the mass, and you're going to see that in one of the homework problems more likely than not. So here we have an unstretched spring, and we're going to go ahead and we're going to put a 10 kilogram mass on there, and what we're kind of looking for is we're looking for, well, how far did this guy stretch? So let's talk a little bit about the force that we're experiencing. The force is going to be the weight, not the mass, which is going to be the mass times gravity, so 10 times 10, or 100 newtons. And what we're looking for is the distortion, so we're going to say F is equal to kx, and the negative sign, I'm just not going to worry about that because I know what the direction is going to be. And so we're going to say x is going to be equal to the force divided by k, so that's going to be 100. divided by 5, and I'm going to get 20 centimeters. We can take this a little bit further than springs, and we can talk about real physical bodies, and we can talk about tension and compression. If something is being pulled apart, we're going to say that it's under tension, and when it's being squashed, it's going to be in compression, it's going to be compressed. Kind of makes sense. And if we had a steel girder or something like this, and we put this big heavy mass on there, then there's a good chance that it might bend it if the weight was enough, or if this was flexible enough. And let's just kind of think about the atoms here. Well, right on the very tippy top, these atoms are being pulled apart, right? They're kind of being ripped apart from their initial, before this guy was bent. These guys were kind of equally spaced. And so right up here we would say that it's under tension, and right down here these atoms are going to be under compression because they're kind of being rammed together, so they're being squashed. So right down here we're going to have compression. So make sure that you're able to identify regions of tension and compression based on just a picture like this. Now, the one thing to pay attention to is you see this blue line right here, kind of that dashed blue line. That actually has a special name, and that's actually called the neutral layer. And what this layer is that's going to be a region of neither tension nor compression, and in general for uniform stuff it's going to be in the middle of the beam, so that's going to be the neutral layer. So no tension, no compression. Maybe just take a second and think about this picture and see if you can identify regions of tension and compression. So thinking about the atoms right on the very tippy top right here, it looks to me, I don't know about you, but it looks like these guys are being squished together. So there's going to be compression right here. These guys right here in the bottom, well, they're just kind of being pulled apart. So there's going to be tension right here. And there is always going to be a neutral layer where there's no tension nor compression. Now, if you've ever cut a tree branch, then you know exactly what this question is kind of going after. Suppose you drilled a hole through this tree branch, and you can drill it to the top, in the middle, or at the bottom. Where will it weaken the branch the least? Well, remember this branch has got some weight right here, so it's kind of being pulled in that direction. It's kind of stretching these guys out right here. So it's going to be tension right here, and there's going to be compression down here. These guys are kind of being rammed together. And there's going to be the neutral layer right in the middle. Now, I don't know if you ever cut a tree before, but if you cut right here, it's going to start to splinter. So probably not the best place to do it. If you've ever tried to cut a tree branch from below, I really don't recommend it. There's going to be compression, and it's going to bind up on your saw, and your saw is going to be stuck, so you're going to need a spare to get you out. So it's not going to be near the bottom. So it's going to be near the middle. Why? Well, that's the neutral layer. There's no tension, no compression, and that's where it's going to weaken the branch the least. Now, kind of the application of the previous question, you may have been thinking that was a silly question, but construction actually uses this idea when they use I-beams. If we were to use a nice solid beam, so if we were to kind of fill this guy in, then you have to kind of ask yourself, wait a minute, this neutral layer right here in the middle, there's not really tension, there's not really compression, so this beam is not doing a whole awful lot. But with all this steel right in there, that's adding a whole lot of weight. So as I go ahead and I make a building, right, I put layer on top of layer on top of layer on top of layer, well, what happens is I'm getting more and more and more and more weight down here. So guess what? I need to reinforce this guy. So I need to reinforce this. Now that's more weight, so better reinforce the bottom like a bazillion times, and that gets really, really, really heavy. So kind of the solution to this is just to take your I-beam and hog it out right here and reduce all that weight, and we're not really compromising the strength of the I-beam, because the top is where the tension is, the bottom is where the compression is, and we're minimizing the weight. Let's take a look at one practical application of compression, and that's going to be arches. So arches are based on compression. Now, if you take a look at some older buildings, ancient Greeks and Romans, they built beautiful buildings like this guy right here. But in order to support the roof, they needed all these columns. All of these guys were designed to support the roof. But once we discovered arches, then all of these supporting columns really weren't necessary. Now, why is that? Because stone and concrete are very withstand, or they can withstand compression very well, and actually it even increases the strength of the structure. And kind of take a look at this guy. I'm going to kind of exaggerate these two guys right here. If we were to put a load on this guy right here, well, what's going to happen is this guy is going to push outwards in that direction, that guy is going to push outwards in this direction, and we're going to work our way down the structure right here. So take this little chunk of it right here, and this guy's got some load on it. It's got some load on it from that side. It's going to push down on there. The same is going to be true over here. Kind of draw these guys right over here. Got some load. It's got this guy pushing on it, and it can push in that direction. And at the end of the day, all of the pushing essentially gets worked its way down out away from the middle and down the sides. So all of the pushing kind of works its way, and it's supported just by this side and by this side right there. So it's kind of naturally strengthening it because it's forcing it together, and you don't even need to use concrete on something like this. So compression, very important for arches. One special type of arch, just getting some jargon out of the way, is called a catenary, and that's just an arch that supports its own weight. For example, the Arch of St. Louis right over here. My dad and I drove by that once, and kind of the funny thing is the shape of a catenary is the same exact shape as a chain that's being held upside down. So you can kind of see this guy right here, actually the author's son, and he's holding this shape right there, and that looks exactly like this catenary in reverse. So it's the natural shape of a chain that hangs between 2 points. If we took an arch like a catenary, we just kind of rotate it about itself. So take an average everyday catenary and rotate it 360 degrees. Then you just have a dome that supports its own weight, kind of like the Jefferson Monument that you see right here. Now the last concept I want to cover is that of scaling, and that's really when we're taking a look at, well, really what we're kind of taking a look at is we're taking a look at the strength, thank you, strength to weight ratio, so an S to W if you will. And it turns out that strength is going to depend on the cross-sectional area. Weight is going to depend on the volume, right? We can kind of do a density thing, density is mass to volume, and kind of work our way to weight. So this guy is going to depend on volume, strength is going to depend on weight, and when we take a look at essentially the ratio of the strength to the weight, because surface area is going to go like size squared, while volume is going to go like size cubed, this strength to weight ratio is going to go like 1 over size, and interestingly enough this ratio decreases with increasing size. So if we were to take a look at something that's kind of small, maybe something that was a centimeter cubed, and take this 1 centimeter cubed and fold it out, then the surface area is going to be 6 and the volume is going to be 1. If we looked at something that was 8 cubic centimeters, so something that was 2 by 2 by 2, fold that square out, and the surface area is going to be 24, the volume is just 8, and this ratio goes down to 3. Now, kind of the implications of this is, have you ever seen how something really small, like an ant, can carry a huge load? Like an ant can carry something like 10 times the size of it, but if you had an elephant, oh, this one's going to be bad, and that elephant can't carry 10 elephants, it probably can't even carry a single elephant. So kind of what's going on is, as we scale up to larger and larger things, this strength to weight ratio goes down. So an ant is small, so it has a large strength to weight ratio. An elephant is big, it doesn't have a large strength to weight ratio.